Hello everybody. Have you ever wondered why carbon dioxide is linear and water is bent in shape? Well, to answer this question, I'm here to discuss the important concept that's VSEPR theory. My name is Feroz Ahmed Tedi and I'm going to discuss valence shell electron pair repulsion, that's VSEPR theory. To understand this theory, let's first take the example of three molecules, that's methane, ammonia and water. According to valence bond theory, we have to check its steric number first. So the steric number, as we know, the steric number is equal to total valence electrons plus number of monovalent atoms divided by 2, which is total valence electrons plus number of monovalent atom and its half. So let's first calculate the steric numbers of these three molecules. In methane molecule, the carbon having 4 valence electrons plus 4 monovalent atoms divided by 2, which is equal to 4. In case of ammonia, nitrogen having 5 valence electrons and 3 monovalent atoms, and its half will also be equal to 4. And in case of water, the oxygen having 6 valence electrons plus 2 monovalent atoms divided by 2, which is also equal to 4. Which shows us that hybridization of these three molecules is sp3. So, the valence bond theory predicts, according to hybridization, the geometry of the molecule. If we look at these three molecules, the geometry of these three molecules is tetrahedral, according to the hybridization and valence bond theory. So, their geometry will be, this will be also tetrahedral, and this will also be tetrahedral, this will also be tetrahedral. Now, if you look at their shape, considering this hybridization, let's look at their geometry. So the geometry of methane molecule will be tetrahedral. Similarly, in case of ammonia, it will also be tetrahedral, and in case of water, it will also be tetrahedral like this. Now, we know in tetrahedral the bond angle is equal to 109 degree and 28 minutes. So, according to valence bond theory, the bond angle between them, this alpha should be 109 degree 28 minutes. Similarly, in case of ammonia, it should be 199 degree and 28 minutes, and similarly in water molecule. But it is found to be the bond angle between ammonia is alpha is found to be 107 degree, and in case of water molecule, it's found to be 104 degree 0.5 degree. So why this is this kind of anomaly? So why this happens? Why bond angle decreases and why there is a perfect bond angle of the tetrahedron? So this unusual behavior, or we say the decrease in bond angle, is understood and is explained by VSEPR theory. If you look at these three atoms, let's have a look at this methane molecule. There are only present as bond pairs. This electron pair, this is the electron pair here, this is also an electron pair, this is also an electron pair, and this is also an electron pair. If you look at this molecule, we have 4 electron pairs that is taking part in bonding. So this is taking part in bonding. While in case of ammonia, there are only 3 electron pairs that are taking part in bonding, and 1 electron pair is that's not taking part in bonding. We call this electron pair as lone pair. Similarly, in case of water, there are two lone pairs, and there are only two kind of bond pairs, two bond pairs and two lone pairs. So this turns out to be that the bond pairs, the electron pairs are different in case of methane, in case of ammonia, and in case of water. So VSEPR theory explains that the different electron pairs have different kinds of repulsion. First, the VSEPR theory says that these electron pairs have the kind of repulsion. They keep repelling from each other. So they kind of move away from each other, and this creates a distortion in their shape. Now, if you look at their bond angle, we have here only 4 bond pairs, but in case of ammonia, we have 1 lone pair. So the VSEPR theory explains that this lone pair has more repulsion than these bond pairs. That's why this lone pair pushes these bond pairs away from it. That's why the bond angle decreases. Similarly, in case of water molecule, the lone pair keep repelling from each other. This in case constricts the bond angle between the bond pairs. This is the reason why bond angle keeps decreasing when the lone pairs keep increasing. Now let's come back to the VSEPR theory. What VSEPR theory is now? VSEPR. VSEPR stands for valence shell electron pair repulsion. So what this means, it consists of many postulates, and I'll try to explain them. Have a look at this water molecule. We have 2 lone pairs here. This is called a lone pair. This is also called lone pair. What lone pair is? Lone pair doesn't take part in chemical bonding, or it doesn't form a chemical bond. While this is but these are bond pairs. A bond pair is an electron pair which is shared by 2 atoms. Now, according to VSEPR theory, these electron pairs, we have 4 electron pairs here, 1, 2, 3 and 4. These electron pairs keep repelling from each other. So this creates a distortion in its geometry, and the VSEPR theory explains or predicts its shape. What its shape after the repulsion. Now the first postulate of the VSEPR theory is that these electron pairs keep repelling. And the second postulate explains that this repulsion is not similar for the bond pair and the lone pair. The repulsion between lone pair and lone pair will be maximum. So this repulsion will be more, and which means that repulsion between lone pair and lone pair will be maximum, and which will be less in lone pair and bond pair, and finally the bond pair and bond pair. So the second postulate explains that the repulsion between lone pairs, this lone pair keep more repelling because it's the electron pair is present on the single atom, while in case of this bond pair, their repulsion is not that much. That's why the lone pair repulsion is more, which leads to the decrease in the bond angle of the molecule. So the shapes of the different kinds of atoms and molecules is predicted by this theory. Now the third postulate explains that if lone pair is not present, is absent. If lone pair is absent, then geometry is equal to shape. Let me take an example of methane molecule. We have C, H, 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 and H. As you can see, there are 4 electron pairs here. and the 4 are bond pairs. This is bond pair, this is bond pair, this is bond pair. No lone pair. Lone pair is equal to 0. Bond pair is equal to 4. So its geometry is tetrahedral, and also its shape will be tetrahedral. Now, what is the difference between geometry and shape? This is this simple difference. Geometry involves both lone pair plus bond pair, while in case of shape it involves only bond pairs. This is the major difference between geometry and shape. Now let's take the steric numbers one by one. First we will take steric number 2, then 3, then 4, and then 5. Okay, I have drawn the table. Now let's take the steric number 2. What steric number 2 means? That two surrounding atoms are present and there is a central atom. There are two terms, central atom and surrounding atom. Central atom is the main atom and surrounding atoms are the atoms that are present around it. So in steric number 2, there's a case of 2 0 lone pair and 2 bond pairs. The geometry will be linear like this: A, B, B, and the shape will be A, B, B. This is proved by valence bond theory. And its example, for example, beryllium chloride, BeCl, Cl. The shape will be linear, and also its geometry will be linear. This is for steric number 2. Now let's take steric number 3. There are two possibilities for steric number 3. Either there are 3 bond pairs and 0 lone pair, or there is 1 lone pair present and 2 bond pairs. First let's take when 0 lone pair is present and 3 bond pairs are present. So when 3 bond pairs are present, which means geometry will be, for 3 the geometry is trigonal planar. So the shape will be like this: A, B, B, and B. Also we learned that when the number of lone pair is 0, which means geometry is equal to shape. The shape will be same, trigonal planar. So the shape will be like this: A, B, B, and B. Now its example, let's take an example of BF3. Now, the second case arises when 1 lone pair is present and 2 bond pairs are present. So we will try to predict the shape through VSEPR theory. When the number of lone pair is 0, when the number of lone pair is 1 and the number of bond pair is 2. So the geometry will be same because the steric number is still the 3. So the geometry will be trigonal planar. Like this: A, B, and B. But the shape will not be the same, trigonal planar, because the lone pair isn't counted in the shape, only bond pairs count. So the shape will be like this. If we hide this, the shape will be like this. This is kind of a bent shape. So if we try to erase this, this is kind of a bent shape or V shape. So in case of this, there will be bent shape. This is called bent, or this is called angular or V shape. Now its example, simple SnCl2, NCl having like this. Now a point to remember: in trigonal planar the bond angle is 120 degree, but as a lone pair is added, lone pair pushes these bond pairs towards themselves, so decreasing the bond angle. So this bond angle is around 90 degree. Should it be around 120 degree? But this is not 120 degree, this is 90 degree only. Why? Because of the presence of lone pair. Now let's take steric number 4. Okay. In steric number 4, we have many possibilities. First, let's take the possibility of 4 bond pair and 0 lone pair. We have 0 lone pair and we have 4 bond pairs. So when we have 4 bond pairs, or when the steric number is 4, according to valence bond theory, we have the geometry of tetrahedral. So we have geometry like this: A, B. Since the lone pair is 0, the shape will be similar, tetrahedral. Example, similar CH4. Now, moving on to the next one, that's when the lone pair is 1 and bond pairs are 3. We have got 1 lone pair, which means that geometry will be same, tetrahedral. Geometry will be like this, but we will try to replace this. This will be replaced by a lone pair here. So the geometry will be same, but now the shape will not be tetrahedral. The lone pair isn't included, so this looks like a pyramidal shape. So the shape will be pyramidal. Now what's this example? Yes, you got it right, ammonia, like this. This is kind of a pyramidal shape. Now, there is another possibility of 2 lone pairs and 2 bond pairs. As we know, steric number is 4, so the geometry will be tetrahedral. This will be like this: A, B, S, B, and B. But the shape will not be tetrahedral. The shape, we hide these lone pairs because the lone pairs doesn't include in the shape. The shape will be, this looks like a bent shape or V shape. So the shape will be bent like this. And the example is classical, like O, H2O. That's why you got the answer that water has a bent shape. Now, let's take steric number 5. Now let's take steric number 5 here. In steric number 5, we have 5 pairs of electrons. So let's take first that 0 lone pair and 5 bond pairs. This is the first case. In this case, we know for steric number 5, we have the geometry according to valence bond theory. We have TBP, trigonal bipyramidal. How does the geometry look like? This looks like this: A, B, B, B. This is in one plane, and this is a pyramid here, pyramidal shape. This is in one plane here. This is a plane, and these are 2 pyramidal. Now, since the number of lone pair is 0, we have the shape similar to this. So the shape will also be trigonal bipyramidal. There will not be some other shape, or because there is no lone pair. So what is its example? Its example is PCl5 or PF5. P like this, Cl, 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 Cl. Or we can take PCl3F2 or something else. Now let's take one lone pair and 4 bond pairs. The geometry will be same, trigonal pyramidal. But let's replace this bond pair by a lone pair now. We have this bond pair here. We replace this by a lone pair. So this one bond pair is replaced by a lone pair. But if you look at the shape will not be trigonal bipyramidal now, because we don't take this lone pair, we don't include the lone pair. So when we hide this lone pair here, we can see that this is the shape of a seesaw, like this. A, B, B, B and B. This looks like an inverted seesaw. If we turn this around or rotate this, this will be like a seesaw. So this shape is called seesaw. Now its example is SF4. S like this, F, F, F and F. Like this. So this will be a seesaw shape. Now here comes another case. When the number of lone pairs are 2 and number of bond pairs are 3. Let's take this, what happens here. If the number of lone pairs are how many? Now the number of lone pairs is 2 and number of bond pairs is 3. So the geometry will be same, trigonal bipyramidal. So we replace the lone pairs here. We have like this, A, this is the geometry. This is also called trigonal bipyramidal. But if we look at shape, we hide these lone pairs. This shape comes to be like a T shape. This is a T, so we call it a T shape. It will be like this, A, B, B and B. Now next take its example as ClF3. This Cl, F, F, F. This will be the example of that one. Now there is a last case, when the number of lone pairs are 3 and the number of bond pairs is 2. Let's see what happens there. Number of lone pairs is 3 and number of bond pairs is 2. Similarly, the shape will be trigonal bipyramidal, but we replace this one by a lone pair here. This will be the geometry as trigonal bipyramidal. But if you look at shape, let's hide these 3 lone pairs. The shape comes out to be like this, A, B, B. And this, you know, is a linear shape. For example, I3 negative. I, here. Negative. So this was the final case of steric number 5. Now let's take steric number 6.